definition of the Kepler problem. That's what we're going to do today. And so Newton invents, modern mechanics, and he has to show that with the law of gravitation, you actually get Kepler's laws out, Kepler's laws of motion. He had inserted Kepler's third law to derive or to discover the law of gravity. So I'm just going to start off with what we had on the board last time. We'll rederive a bit of it. So we had, for the energy, we've already transformed to plane polar coordinates. We've already taken that part of the kinetic energy, plugged in the P dot. This is the U effective of R. And what we're also going to use is U of R minus alpha divided by R. Alpha is a constant involving gravitation constant stuff. So that's going to be the potential. And I'll even remind us of what that graph looks like for the effective potential, to make sure we know that. Effective. It looks like this. Vanishes out to infinity, has a local minimum R sub 0, energy that goes along with it. And that, all that stuff that we discussed last time. So we're going to do the quadrature on this, so I'll rearrange this again. So we're going to have dr over dt 2 over m e minus u L squared 2m r squared. This time we're just going to go through with the entire calculation plus or minus right there. And we're looking for R of phi. Okay, so we're looking for the trajectory. We're looking for the path that the body takes. So we're going to also use L. No, sorry. We're also going to use the chain rule here. So dr dt equals dr d phi dt. But we have for mr squared phi dot equals L. So we have phi dot there, so that's dr d phi. And then the phi dot is L over mr squared. So we'll make that substitution on the left side here. And we did that last time, but that's all right. So we have dr d phi L over mr squared equals plus minus this square root and what's in there. And now we do the separation of variables. So we'll have d phi equal, we'll leave some room here because we're going to write the integral sign in a minute anyway. But so we've got the d phi and we've got the dr. And we're going to leave this kind of an improper fraction for the moment. Okay. So we've got the plus minus, and we've got all of this here. 2 over m e minus. And at this point I'll go ahead and plug in the negative alpha over r. Okay. I'll plug that in right here for the u of r. So e plus alpha over r minus L squared over 2m r squared. Because now we're doing the actual Kepler problem. We investigated this independent of that the other day. And I'm even gonna do the integration of phi. Okay. Because this is the integral we now actually have to solve. So upper bound on this integral is r. These are all prime, but I'm not going to worry is an interesting integration that we have to work on, okay? So what we're going to do is the following. So we're gonna let u, because we're substituting in lowercase u, equal 1 over r, du equals minus 1 over r squared dr. So you see, that's gonna change things up immediately. And b is equal to, we still have a plus or minus. We got the minus sign there, still just write plus or minus in front, that's no problem. I can pull out the L over M and see what we have in our, like that. See what we have in our integral now. So we've got the du, because the dr is r squared du cancel out. So the dr over r squared is the du. So put the du here. We've got 2 over m e plus, and then the 1 over r is the u, so plus alpha u, got square root, minus L squared over 2m, and then u squared. So this will simplify if we invert this in the denominator, m over L, and multiply through. Okay. So this we're going to simplify a little bit more. We've got plus minus integral du. So what we're going to get here, see, I'm just going to invert this and multiply in. So I'll have under the square root 2e m, right? Because that m squared is one of those over L squared plus alpha. I think that was just right, this is alpha 2 over m squared over L squared. So we have 2 alpha m over L squared. U. And here, it's nice, 2 cancels, and the L squared over m squared cancels, so we just have minus u squared. So this is one where we can complete the square. So that's our next task. We'll just keep going here over on this side. And let's see what we get. So we've got b plus or minus eu, and I've got the 2em over L squared. And I'm gonna leave a little bit of room here. And for this, I can do minus, let's just write this down first. So minus u minus 2 minus alpha over m L squared. Alpha m over L squared. Squared, okay. So what do we get here? We get u squared, 2 alpha mu over L squared. Okay. Minus times minus is plus, that's good. So we're subtracting off an alpha squared m squared over L to the 4th, so we have to have plus alpha squared m squared over L to the 4th. I'll put parentheses around this thing here. And keep substituting. So now, this looks pretty heavy-handed, but we're gonna let W equal U minus alpha M over L squared divided by the square root of this thing here. 2E M L squared plus alpha squared M squared over L fourth. Because dW is du divided by this whole thing here. And when we make that substitution, we're going to get this square root in the numerator integral dw 1 minus w squared, and the same thing in the denominator. So let's see if we make sure that makes some sense. So basically I factored this out in front of the integral, and then I had times 1 minus this thing right here squared. Okay. So I factored this out in front of the integral, that's why it's right there. 2E M L squared, L squared, M squared, L fourth, and ditto up there. Okay. That came from the dW, the du equals dW times that. So that came out front as well. So, unbelievably, we've got a plus minus here. We're going to take the minus sign, and we have an inverse cosine. Okay. So what you guys want to do is make sure you have plenty of room in your notes. I'm going to ask you guys to reproduce this so you can follow every step and see what happens there, okay? So phi is equal to the inverse cosine of this W. And now it's just going to be a, pardon me?
You slow down a little, still trying to work out why that works.
Absolutely. Yeah, let's. Here, in fact, this one I crossed out, I'm going to fill in just so that we have no blanks. And we'll absolutely take a little time on this one. Okay. So we have the 2EM squared. And I'll show you where each of these came from. So we had this after we completed the square. This expression here came right out of here. Now, what I'm doing is this is just a constant, right? We just give it a name. It's just a big constant, so I'm factoring it out, and then I have square root of 1 minus this square root that I factored out, but underneath the integral, it's squared. Okay. So when I call this W and I do W squared, right, so I just, it's awkward because it's so big, but it's just a constant. Yeah, usually you don't see a substitution that has that much going on in it. Okay. But remember, this is just a constant, so we could have just given it a new letter name. And making that substitution, then again, dW is just du divided by this constant again here. And so when you implement that, you've got a numerator, denominator, they cancel. And you literally just have integral dW over root 1 minus W squared. So if we take the minus sign, we've got the inverse cosine. Okay. So yeah, like I said, leave room in your notes for that, and I think I'll assign this in some form so that you just go through it really carefully. And what happens from here on out is that we reverse all of these substitutions. We'll take the cosine of both sides, and then we've got this u minus alpha m over L squared. And this is what we have to work on, but this is going to simplify. Plus have to simplify this. We already know that this u is gonna be one over r. We could put it in there at this point if we want to. Let's do that. Okay. So we knew that u was the one over r. So what we're after now is r of phi. And we'll do a couple of simplifications, or we'll rename some stuff before we do that. Good, so. Here we go. We're going to leave it in this form for the moment. We have alpha m over L squared here. Okay. So cosine b, we've got 1 over r minus alpha m over L squared. Now this, apparently we can pull out an alpha m over L squared. And then we have a square root. If we pull that out here, 1 plus 2em over L squared, I'm going to multiply that out, alpha. Alpha squared, m squared, L over 4 like that, just to see what comes out here. So there we have 1m L squared, 2L squared over m alpha squared. So 2 L squared over m alpha squared. Yeah. So once more. Cos b equals over r. Oh, and now we can cancel that. So we'll have L squared over m alpha 1 over r minus 1 divided by root 1 plus 2e L squared over m alpha squared. So what we're doing is we're putting this into a standard form. Okay. So, and this is pretty close to the standard form now. Good, so let's see. Put a box around here. We're going to name, let P be equal to L squared over m alpha, and E be equal to this expression at the bottom, 1 plus 2e L squared over m alpha squared. And if we use this, okay, this P and this E here, this thing simplifies, and then we can analyze it and see what it is that we found. These intermediate steps, of course, we're not seeing anything, okay? But now, you're gonna see we have E cos phi, E cos phi by cross multiplying is equal to P over R minus 1. And P over R is equal to 1 plus E cosine of phi. And finally, R is equal to P divided by 1 plus E cosine phi. Okay, so this is the point at which we declare victory, although we don't see what we've won yet. Okay, but that's the actual form that we were looking for. And now we're going to have to go analyze this thing. Okay. And these things will all have a very interesting meaning. So up until now, we were just doing a calculation. Make sure you leave a lot of room and try to all sign good, so this turns out to be the polar form of the conic sections. So we're gonna prove that this is the elliptical orbit that we were looking for, and we'll do that step by step. So let's consider this whole calculation a success, and I'll just hold on to all of our ingredients now, write them all down, so that they're all in one place. So let's see what we'll list here, actually, we'll list here everything in some form. So we started out with this, so plus u of r, so minus alpha over r equals E, and this was the effective potential, okay, u effective of r. So that's the first thing. And then we have this P is called the parameter L squared over M alpha. E is the eccentricity, which we'll see in a minute, 2E L squared over M alpha squared, eccentricity. And then R is equal to P over 1 plus E cos phi. And just to remind us, what is this R? That's from x equals R cos phi, y equals R sine of phi. Okay, so now we have everything in front of us, and we can just systematically analyze it and make sense of it. Good, right? This is the plane polar coordinates, R of phi. So we don't have R of t and phi of t. We have R of phi. So let me put here as a note, just for the orientation. Since this is R of phi, we have m r squared phi dot is equal to L as another differential equation, right? And so you can get, via the chain rule. We're actually not going to go here, but just to point out that this is not R of t, it is R of phi. And that's, we're going to prove that's an ellipse. Yeah, the polar form of the conic section isn't something that we just have at our fingertips, right? How about you guys? No. So we'll have to be a little systematic to work our way through this. But starting our analysis, what would a circular orbit be? Remember, the circular orbits were the simplest ones. So let's begin with circular orbits. So there's our equation of the orbit right there. How do we turn that into a circle? When is this thing a circle? What characterizes a circle? R is constant, right? So when would R be constant here? R of phi be a constant? So we gotta analyze this thing. So when would the radius be constant? Here on the left, it's when it doesn't depend on phi, which means this E has to be equal to 0. So for a circular orbit, let's put this in words. For a circular orbit, R naught equals constant. So E has to equal 0 right here. That's interesting. So E equals root 1 plus 2E L squared over M alpha squared. And for that to equal 0, the energy has to be negative. And we had actually seen that the other day, right? Negative energy for bounded orbits. So then what do we have? E equals minus m alpha squared over 2L squared. There's a little question mark there. What's going on? And R equals R0 equals constant. But this R sub 0 is the minimum of the effective potential for circular orbits. So let's go recall U effective equals L squared over 2mR squared minus alpha over R. And I'm even going to sketch it because there's your R0 and there's your E sub 0. So both of these quantities are something we actually had without doing this calculation, and let's make sure they work out. So R sub 0 is the point, is the radius that minimizes the effective potential. So we'll take the first derivative, U effective prime is equal to minus L squared over M R cubed plus alpha over R squared. And sure enough, that equals 0 when R naught is equal to L squared over M alpha. That make sense? Okay. So that's when this equals 0. You factor out an R cubed. Do 1 over R naught cubed L squared over M. Alpha R naught. So good. R naught is L squared over M alpha. And look over here. E is L squared over M alpha, which is the parameter. So that's the radius of the circular orbit. And then there you have it, right? The E is 0, R is equal to P is equal to L squared over M alpha. So that's where the circular orbit came in, or comes out. Of course, this circular orbit business we already knew last time, right, from that analysis. But of course, it has to be contained in this general expression here. So there we're in good shape. And the value of that minimum energy is also going to be available to us. So now we have this R sub 0, and so I'll just write here also E sub 0 is equal to U effective evaluated at R sub 0, as you see in this graph and by definition. So we'll have minus L squared over M, and we have to do this R0 cubed. So R0 cubed would be L to the 6th M cubed alpha cubed. I should have had an alpha down here. And then we'll have plus alpha over R naught squared, so L to the 4th M squared alpha squared. Actually, wait a minute, what I got here? Plus alpha over R naught squared L to the 4th. Alpha squared two.
Yeah, you would try to get
What
this
I-
squared over two n r squared minus alpha over r.
Yeah, you know what, I'm mixing up my metaphors.
Yeah.
Oops, I'm mixing up the neutron. I'm going back to U. Actually, there we go, so that was the problem. So it's L squared over two M and this R naught squared, which is L to the fourth M squared. Alpha squared, that's better. Minus alpha over R naught, which is L squared. L to the fourth. No, L squared, my bad. Alpha over L squared M alpha. There we go. So we're going to be left with negative 1/2 of this alpha squared, M alpha squared over L squared. Because we have plus a half minus a whole, so we're left with negative 1/2. And of course, that works out as well. So those parts of the analysis were already available to us before we solved the integral, just on the analysis of the effective potential, but here we have them right here. Good, so the circular orbits we've taken care of. And we're consistent with the old analysis of the circular orbit. So what we have to do next is somehow understand that this is an ellipse, because Kepler's law was that the orbits were ellipses with the sun at one focus. Good, that took care of the circular orbit. So I'm gonna erase that and leave that stuff up there, and we'll see how far we get. That was just a consistency check. Okay, so what about the rest of this analysis? So the next thing we're going to do is we're gonna do a graph of R of phi. The graph isn't gonna prove the ellipticity yet, but now we're gonna take the case where E is not equal to 0, and remember we have X is R cos phi, Y is equal to R sine of phi. And so we'll go ahead and get a sketch here, not too small. So when phi is equal to 0, we chose our integration constant to make phi equal to 0 on the positive x-axis. Phi equals 0 when R is equal to R min, as we'll see in a moment. And then when phi is equal to 0, cos phi is 1, x is equal to p over 1 plus e. We'll do a p over 1 plus e right here. And when phi is equal to pi, we've got a minus 1 there, we're over here now, and it'll be p over 1 minus e. Or I could say, and I'm gonna make it nice and exaggerated, so negative p over 1 minus e. Okay, so those are 2 points of our graph. Now, the other 2 points we can easily get is when phi is equal to pi over 2, because then we've got a 0 here and a 1 here. So when phi is equal to pi over 2, we're going to have, I'll put it right here. So phi is equal to pi over 2, we have R of phi is just equal to p. And minus p over here. Now what's going to happen is at the geometrical center of this thing, we're going to get some elliptical, harder to draw than it is to understand. We're looking for something like that. The point here being that we're not yet at the maximum Right? P is not the maximum of that curve. That maximum takes place up there. And negative P is not at the minimum over here as well. Okay, so it's a little hard to draw, but you get the idea. So what we're trying to do is find y sub max. So find maximum value of y, and so we'll have y is equal to sine phi times this r, so it's p sine phi over 1 plus e cos phi. So to find the maximum value here, we're going to do the first derivative criterion, dy d phi, and set it equal to 0. So that's equal to p cos phi 1 plus e cos phi plus p sine of phi negative 1 plus e cos phi squared. We'll just simplify this and see what happens. So get a common denominator of 1 plus e cos phi squared, and then we'll have e cos phi 1 plus e cos phi minus p sine phi. I'm not done yet, am I? Hold on. Let's return. So cos phi 1. This one was p sine phi negative 1 plus e cos phi. I had to have negative e sine phi. I missed the derivative on the chain rule. Sine phi negative 1 cos phi. Okay, good. So this time we'll get that common denominator, same common denominator. 1 plus e cos phi squared. We'll have p cos phi plus p e cosine squared phi plus p e. There's p, there's negative in there, plus e sine squared phi. So this is simplifying. This will be p times cos phi, and these two add up to 1. Cos phi, so p cos phi plus e over 1 plus e cos phi squared. Okay, good. We want to set this equal to 0. And this equals 0 when the numerator is equal to 0, comma, so equals 0 when cosine of phi is equal to minus e. Remember, e was always positive, it was that square root there. So e is always positive, cosine of phi is equal to minus e. We'll see on our sketch that already makes sense because we're looking at the phi that's in the second quadrant, the cosine there is negative. Good, so we're in good shape. Now we just have to calculate y max equals p sine of phi, and I'll show you the steps. Sine of phi 1 plus e cos phi. So what we do is we do p root 1 minus cosine squared of phi. So that's an identity for the sine of phi 1 minus cosine squared. And then 1 plus e cos phi. And now we can plug in what cosine of phi is. It's negative e. So it's p times the square root of 1 minus e squared divided by 1 minus e squared, because cosine phi itself is negative e, okay? I'm gonna block this off for you. So this is p divided by root 1 minus e squared. we gotta assemble some more of our results. Okay, this was just a calculation to figure out what y sub max is. Y max, which we needed to know. So having that, I'm gonna erase some stuff. I'll put that here. Right. Now we have y max e over root 1 minus e squared. Not yet an ellipse, but we're getting there. We're getting there. So we found y max. Okay, if I erase this now, you guys have this? Good. So now, I think we got just enough minutes to get to a good point. So now what we have is, we haven't shown this yet, but this is going to be the semi-major axis of the ellipse, and this is going to be the semi-minor axis. Because this first one corresponded to R min, okay? So what we have is 2a is equal to p over 1 plus e minus negative, so plus p over 1 minus e, p times 1 minus e, plus 1 plus e, 1 minus e squared. So those cancel, equals 2p over 1 minus e squared. So the semi-major, so a is equal to p over 1 minus e squared. And we just found b. And b is equal to p over root 1 minus e squared. Squared. And yeah, we're gonna make sure we call this the semi-major axis. Semi-major axis. Semi-minor axis. And of course, there's all this physics hidden in here, but we're just assembling all these pieces for now, okay? So now we have assembled these two, and the next thing we're going to have to do, we have to prove that this thing here, p over 1 plus, or r equals p over 1 plus e cos b is an ellipse. Now the equation of the ellipse that we're used to has to be centered right there on the geometrical center. So I'm going to name this little thing d here for the moment. D. This d is the distance from here to the actual geometrical center of the ellipse. Because then we can say x plus d squared over a squared plus y squared over b squared equals 1. Okay. You guys are familiar with this, x squared over a squared plus y squared over b squared equals 1 as the equation of the ellipse. Are you familiar with that? So the ellipse centered on the origin, let me go ahead and write that down. We're about to end here. So the ellipse centered on the origin, x squared over a squared, y squared over b squared equals 1. That's the equation of the ellipse centered on the origin. And because ours is centered to the left of there, we have to do x plus d. And we still have to find out what that d is. It's not going to be difficult. So we have our work cut out for us. And some of that work is yours. So this is going to be a homework, but let me put this down for homework. So for homework, the first thing I want you guys to do, and, you know, we'll work on this together next week too, you want to reproduce the integration that led to this here. Okay? Just want to reproduce it on another, you know, another sheet of paper and make sure you really understand every step. So, I'll just write your calculation that leads to what we're calling star right over there, right, the RFP. And then the second part of it is to prove that this equation star is an ellipse. Yeah. So if you need something to work on, you know, over the weekend, then you've got something, you know, you just return to this thing and make sense of it, because you have to see it more than once. You have to see it more than once for it all to make sense. Because there are a lot of pieces in here, and right now, you know, it might be looking like a bit of a confusion. But, what we're going to do, we're gonna, you know, set things up and systematically have the whole chart in front of us, right? The entire problem eventually, and then it'll make complete sense. And because it's the Kepler problem, it doesn't get any better than this. It is a very important problem in physics. Good, there you have it. So we'll leave it at that. And like I said, give this a try.